this working? Test. Test. Come on. Come on. Testing, testing. 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 All right, it works. Testing, testing, testing. How's it going? Christopher H. Glad to see ya. Make sure I can see these chats. All right. I think we're ready to go. So today we're going to be reading a paper called RT-2, which stands for Robotic Transformer number 2. And this is a vision language action model. So language as in text, vision as in images, and then action as in robot actions. So this is coming out of Google DeepMind. This is the recently created or joined Google Brain and then Google DeepMind teams. So you can see here in this list of people, you got all kinds of both DeepMind people and originally Google Brain people. Lots of people here. So they have a little GIF here. I actually kind of like this little GIF because it kind of shows you what this entire paper is. So you have a vision language model here, and it's learning from code, learning from newspapers, learning from chess, learning from blah, 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 blah. Code keeps reading. Then Robotic Transformer 1 gets put into it, and then they use it for a robot. And there you go. That's kind of the whole story of this paper. I think this is largely a continuation of the work that we were seeing, for example, with the language models are general pattern machines. This is basically going to be a more applied version of that. So let's go ahead and get started. Authors listed in alphabetical order with contributions listed in Appendix A. So I think once you get to a critical amount of authors on a paper, it starts to get maybe a little bit too hot, and this last slot and this first slot kind of become a little bit too intense. So then what they end up doing is they basically just list in alphabetical order and then give you the appendix here, and they tell you who did what. So you can see how many different people they have working in each thing. A lot of leadership, training, network architecture. This also seems like a lot of people for network architecture. Data collection. These are the people that actually robot wrangle. From the animation, I would assume that it's end-to-end, not using a separate vision model. I don't think it's your end-to-end in inference, yes, but I think that the training is not end-to-end. I think the training is like there's a pre-training and then probably some additional step afterwards. I'm not exactly sure, but yeah, I think the final model is probably end-to-end in that there's no intermediate vision model or control model or anything like that. It's just one model that does everything. Okay. Now let's go back to the beginning. We study how vision language models, so this is something like CLIP, right? Or BLIP, any one of these image captioning models, trained on internet scale data can be incorporated directly into end-to-end robotic control. So end-to-end means basically from the very beginning of the pipeline, which is your images, your sensors, all the way to the other end of the pipeline, which is your actual control, the commands you send to each of the joints of the robot. So that's the two ends of basically the robot pipeline. And whenever you have a language or any kind of machine learning based system that basically goes all the way from the beginning to the end, that's called end-to-end. To boost generalization is just the ability to adapt to tasks that are outside of your pre-training data, right? Generalizing outside of the distribution of data that you were trained on. And enable emergent, this is the word you want to see in a robotics paper. It basically means that there's behaviors that they did not expect and that are basically outside of the distribution of what they're trained on, and they still work pretty well. And here you have semantic reasoning. So semantic is basically just means logical, common sense. So I don't know. We'll see what happens with this semantic reasoning. They're kind of teasing some pretty cool behavior here with emergent semantic reasoning. Our goal is to enable a single end-to-end trained model. This is interesting. Did they actually train it end-to-end? To both learn and to map robot observations, So robot observations are going to be your images and your joints and your sensors, to actions, which are going to be either position control, velocity control. There's a couple different types of control signals that you can send to the motors in a robot. And enjoy the benefits of large-scale pre-training on language and vision language data from the web. Okay, so this kind of is a little bit contradictory here, because it basically, large-scale pre-training on data from the web means that it's not trained end-to-end. It means that it's pre-trained on this stuff, and then it's, I guess, fine-tuned end-to-end. I don't know. We'll see. To this end, we propose co-fine-tune state-of-the-art vision language models, that's quite the mouthful, on both robotic trajectory data and internet-scale vision language tasks. How's it going, Daily? Such as visual question answering. In contrast to other approaches, we propose a simple general recipe to achieve this goal. In order to fit both natural language responses and robotic actions into the same format, we express the actions as text token. This is something that we saw in the other papers that we read previously, such as the language models are general pattern machines, is that you can literally just have the actions of the robot be text and interpreted by the language model as text and outputted by the language model as text, and it basically works. And incorporate them directly into the training set of the model in the same way as natural language tokens. We refer to such category of models as vision language action models and instantiate an example of such a model, which we call RT-2. Okay, so basically they're training a big vision language model similar to CLIP or something like that. I think in this case it's not. CLIP is trying to basically create an embedding space that's works for both text and images. I think here they're more going to take something that's akin to a visual question answering kind of LLM, and then they're going to basically give it a bunch of additional data that is basically robot actions or trajectories. And that's where the extra action is going to come in. Instantiate an example of such a model, which we call RT-2. Our extensive evaluation, 6,000 evaluation trials. This doesn't sound like a huge amount for somebody who's like in the text world or in the image world, but evaluation trials on a real robot take forever, because you basically have to manually reset the environment. You have to put all the things back in the order. You have to basically reset the robot, run the robot again. So 6,000 evaluation trials on a real robot in the real world takes way longer than 6,000 evaluations of an LLM that's done basically automatically. Show that our approach leads to performant robot policies. Policy is just a fancy way of saying the neural net that is controlling the robot at any given time, and enables RT-2 to enable a wide range of emergent capabilities from internet scale training. This includes significantly improved generalization to novel objects, the ability to interpret commands not present in the robot training data, and the ability to perform rudimentary reasoning in response to user commands, picking up the smallest or largest object or the one closest to another object. We further show that incorporating chain of thought reasoning, this is another kind of theme that we're seeing in these language model robotics papers, allows RT-2 to perform multi-stage semantic reasoning. This is kind of badass. So semantic reasoning at multiple stages. I think the multi-stage here is probably going to figure out, or it's probably going to be related to a task that is broken up into different pieces, such as, I don't know, if you want to make an omelet, right, there's multiple stages to that. You have to gather all the ingredients, then you have to prepare all the ingredients, then you have to cook all the ingredients. So I think that's kind of what they're figuring out here, or what they're talking about here. Figuring out which object to pick up to use as a hammer, or which type of drink is best suited for someone who is tired. Okay. I don't know anything about robotics. Does the motor get a signal from the model to take an action? Basically, yes. So, I mean, the motor itself is not actually, you can't actually send a text token to a motor. Motors are controlled by a very low-level chip that basically exists in two possible things. Usually it's basically position control or velocity control. So the actual motor at the very end is just receiving a electrical current, and then the electrical current basically increases, decreases, basically causes more torque, less torque on the actual joint, and then you have a small little controller that's basically using something like a PID controller to basically actually get the position right. But there used to be more levels on top of that, right? More control modules on top of that. And now we're going to basically as close as we can get to the motor, which is sending position commands or velocity commands. Chain of thought reasoning is whenever you add multiple or basically whenever you, I think the easiest way to think about it is in a language model. For example, if you say, explain how to make an omelet, think step by step. So this is kind of the original chain of thought where basically when these LLMs first came out, people realized that by adding something like think step by step and forcing the LLM to basically create its own context like this, and basically it creates its own prompt, it ends up getting better results, right? So basically things that are later on in the answer benefit from having all this extra context in the beginning. And that is what they're going to be doing here with the robot as well, where you can get the LLM to add extra things to the prompt so that it gives it more context and thus performs better on later parts of the prompt. Yeah, no problem, Dave. Thanks for the question. Introduction. High capacity models. High capacity is just a fancy way of saying a big model, so lots of parameters that you can learn, right? Hundreds of billions of parameters potentially. Pre-trained on broad web-scale dataset provides an effective and powerful platform for a wide range of downstream tasks. Large language models can enable not only fluent text generation, fluent has literally no definition here, but emergent problem solving and creative generation of prose and code. The trend towards single models trained end-to-end in robotics is interesting because it's kind of the opposite approach to something modular like ROS. 100% agree, yeah. And as someone who's like had to deal with ROS a lot of times way back in the day, it's very gross and not good at all. And the complexity makes it very difficult for other people to learn. ROS is a robot operating system. And it's basically, yeah, so it was founded in 2007. It originally came out with this robot called the PR2. This was the, let's see, PR2. Yeah, here you go. This was the original ROS robot. And basically, it's like a software framework that deals with all the communication overhead. So basically, a robot that is running ROS, there's many different computers, and all these different computers are all kind of basically in this publisher-subscriber kind of model where you'll have, for example, a vision module. And what the vision module does is it subscribes to the camera module, so it receives images, and then it does some calculation. Maybe it tells you how far away you are from some thing, and then publishes that information. How far am I away from this thing? And then some other module will consume that information. So when you actually have a final robot that's using ROS, you end up having dozens of these little modules that are all basically doing their own little separate computation on potentially different devices and then communicating that. And the idea behind ROS was that modularity is the way to get to a robot that sits in your house, right? Where you would basically have a bunch of different pieces, and then each of those pieces can be improved separately, and then by combining all of these pieces over time, each of the pieces get better, and then finally we get to R2-D2 and C3PO. But what's interesting is that kind of modularity and then improving each piece separately is actually not the way to AGI. And it turns out that the way to AGI is to just have one giant module that does everything, right? So kind of interesting how that worked out. Vision language models enable open vocabulary visual recognition and can even make complex inferences about object-agent interactions in images. Such semantic reasoning, yeah, so it's like expert systems where you need to construct a thing and logic in advance. Makes debugging easy if you're handcrafting everything with the traditional technique. The debugging is quote-unquote easy, but it's not, right? Basically, debugging things in ROS can get very hairy. You basically end up creating these ROS bags, which are basically logs, but like the log, usually in a ROS system, you have the computation is separated over a bunch of different computers. So basically, you have to take all those logs, put them in a thing called a ROS bag. That ROS bag basically plays out to you what happened, and you have all these like race conditions usually, where basically this little module took a little bit longer to do the computation, so the answer that it gave was a little bit stale, and then this other module, which relies on this one, ended up getting the stale answer, and therefore you got a problem here. So there's just so much complexity in ROS that it's, even though it's easier to debug, it's not actually easier to debug because of its just too many pieces. Visual interpretation would be tremendously useful for a generalist robot. Generalist robots is basically the holy grail at this point, because we are so close to creating a robot that you can put in your house, right? And the hardware has been here since forever. So in the original PR2, one of the original kind of demos that they did when they released this robot and when they released ROS is they basically had a guy teleop this robot and do a bunch of things, like basically cook pancakes and do things. So people were convinced that, okay, the hardware is there. We already have the hardware that we need to have a general purpose robot that is very useful. Now we just need to solve the software problem. So we're still at that point where the hardware is there, right? These robots, if you could have a very good intelligence that's generalist inside this robot does not cost that much money, right? I think you could get a robot like this for probably $10,000. This one's obviously way more expensive because these are custom prototypes that are basically made in a very low volume, so there's not a lot of them. These robots are probably hundreds of thousands of dollars, but I think once you have the certainty that you know that it's going to work, I think you let the manufacturing supply chain take care of it, and I think you could probably have robots for single-digit thousands of dollars. Okay. Let's see. It is unclear how robots should acquire such capabilities. It turns out trying to predict the next token in internet data is the best way to do that. While a brute force approach might entail collecting millions of robotic interaction trials, the most capable language and vision models are trained on billions of tokens and images from the web. Yeah, so billions of tokens and images from the web turns out to be a way better way to make a robot learn than millions of robotic interaction trials. An amount unlikely to be matched with robot data. On the other hand, directly applying such models to robotic tasks is also difficult. Such models reason about semantics labeled textual prompts, whereas robots require grounded, low-level actions, such as Cartesian end effector commands. So this is a position control. The end effector is just the very last digit in a robot arm, so the end effector would be just this arm here. And the reason they call it the end effector, it's because it's at the end of the kinematic chain, and then it's an effector because it's affecting the environment. So that's the end effector, is just basically a fancy name for the hand. While a number of recent works have sought to incorporate vision language models into robotics, such methods generally address only the higher level aspects of robotic planning, essentially taking the role of a state machine that interprets commands and parses them into individual primitives. This is what we saw with the Minecraft paper, where basically the LLM is operating at the high level kind of control, where it's basically saying do this, but then in order to do this, you actually then need to execute some hard-coded, crafted behavior, which in the Minecraft world is code, but in the robot world might be like some hard-coded pick behavior, which are then executed by separate low-level controllers that themselves do not benefit from the rich semantic knowledge of internet-scale models during training. Therefore, in this paper we ask, can a large pre-trained vision language model be integrated directly into low-level robotic control to boost generalization and enable emergent semantic reasoning? So another thing to realize is that we're still just scratching the surface of this, right? When they say low-level robotic control, the level that they're referring to is sending a position command into a chip that is basically on the actual motor. But I feel like this is just the beginning, and eventually we're going to get to a point where there actually isn't even any additional chips or hard-coded computation on the motor itself, where basically the direct current that gets applied to the motor is literally what comes out of the LLM, right? So even though right here they're calling it low-level robotic control and low-level controllers, there's still levels below that we haven't even gotten to. We just need to get to the point where this is standard, and then we need to get to the point where manufacturing leads to the point where people are like, hey, instead of having like 50 chips in this robot, why don't we just have one chip, and so on. Okay, let's look at this picture. RT-2, Robotic Transformer 2 Overview. We represent robot actions as another language, okay, which can be cast into text tokens and trained together with internet-scale vision language datasets. During inference, which basically means during runtime when you're actually running the model, the text tokens are de-tokenized into robot actions. So generally these LLMs are consuming not actual text, they're consuming what are called tokens, which are basically the text broken up, and you're going to have some dictionary of all possible tokens. So here they're basically adding to that dictionary and saying, here we're going to add a bunch of tokens that represent specific robot actions, such as here you have delta T, which is translations, right? So you have X, Y, and Z. That's why there's 3 numbers here, delta T. And then delta R, there's 3 numbers here, which is the rotation in the 3 axes. So we live in a 6-dimensional world, or there's 6 dimensions that compose a pose. So you have X, Y, Z, and then the 3 Euler angles. A lot of times the Euler angles are actually not popular. Usually you express it as a quaternion. So that's something to think about here, where they actually probably should have left this as a delta Q, right? A quaternion representation for the rotation, because this delta R is actually misleading. Besides taking the actions, you also need to know the depth, strength during picking as well. Yeah, there's a bunch of extra things as well. So the gripper itself, these are called parallel jaw grippers because the jaws are parallel. This is actually a little bit more, it's a little bit more complicated than a parallel jaw gripper because they actually have some compliance to them. But yeah, you have to basically say either what's the distance between the jaws, that's one way that they can control it, or another way that they control it is basically they just have a close and an open signal, and when you have the close signal, it just closes it until it basically, once you grab the object, it'll start to become very hard to keep pushing, to keep grasping, and when it becomes very hard to keep grasping, the current in the motor will spike. The current will suddenly go up because it becomes very hard to keep grasping, and at that point, either there's a little tiny, basically closed loop system within the gripper itself that determines when the thing is closed and when it is open, or you could actually be outputting that directly. Detokenize just means changing these actions here. You see, think these are tokens here. So these little like cylinder tic-tac looking things, those are the tokens, and then they turn them back into the actual actions. So these are tokens. Transferring some of their generalization and semantic reasoning and understanding to robotic control. So we have a internet scale VQA, which means visual question answering, and then robot action data. So here you have a kind of standard visual question answering data set here, where you have basically a question and an answer and a picture. You have here the same thing but in French, kind of showing you that the way that they're putting this into the data set, that the way that they're adding this robot data into the vision question answering data is they're pretending that it's a different language. So here, que peux-je faire avec ces objets? Faire cuire un gâteau. This is just cook a cake. And here you're basically saying mer 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 in robot language, and it's mer 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 in robot language. So the LLM just thinks it's a different language. Vision language models. So then at that point you can basically say, here's the question, here's the image. The image is actually getting fed through a VIT here, so there's actually this entire thing is called RT-2, but it does actually seem like they have a separate vision image. So maybe to answer your question, Christopher, I think you asked this at the very beginning, it does seem like even though RT-2 is end-to-end, where it's basically taking the original task and the image and then giving you the actual output, within the RT-2 model, there is a separate vision transformer. So This VIT here is probably pre-trained on a bunch of other stuff as well. Cool. All right, let's keep going. To this end, we explore an approach that is both simple and effective. We directly train vision language models designed for open vocabulary, visual question and answering, and visual dialogue to output low-level robot actions, along with solving other internet-scale vision language tasks. We can train them on robotic trajectories by tokenizing the actions into text tokens. So they had to basically decide on some tokenization scheme, and that's actually going to be interesting to see what they pick, because I feel like it's going to have a big impact. Can be directly trained on instruction following robotic policies. This simple approach is in contrast with prior alternatives for incorporating VLMs into robot policies or designing new vision language architectures from scratch. Instead, pre-existing vision language models with already amortized significant compute investment are trained without any new parameters to output text-encoded actions. We refer to this category of models as vision language action models. So they're trying to coin this new term here. We instantiate vision language action by building the protocol proposed by RT-1 using a similar dataset but expanding the model to use a large vision language backbone. Okay. Let me sip on this yerba mate here. We observe that robotic policies derived from such vision language models exhibit a range of remarkable capabilities. They were also using a VIT for MOO. Yeah, I think it's just like there's... The kind of end-to-end, and even we were seeing this in another paper that we read last week where it was called like meta transformer or something, where the words end-to-end and one model, and like people are starting to over leverage and abuse those words, and like here they saying, oh, it's end-to-end and it's only one model, but when you actually dig in, it's really two models. You got the vision transformer and you got this LLM here. So I think it just depends on which way you want to look at it, right? One way to look at it is that, yes, it is one giant big model. And even here, you could look at this large language model and you could say, hey, that's not actually one model. That's like 8 transformer blocks. So I think people are starting to, the words end-to-end and the word one model are starting to kind of like become more fuzzy. Combining the physical motions learned from robot data with the ability to interpret images and text into a single model. Yeah, so here it's like, is it actually a single model? If you think of it as, you could keep zooming in, like what is a single model? I think they're just, terminology is becoming a little bit more loose. Besides the expected benefit of dramatically improving generalization to novel objects and semantically varied instructions, we observe a number of emergent capabilities. Robots know something. The model's physical skills are limited to the distribution of skills seen in the robot data. So this is telling you it's not able to generalize outside of the distribution that it's been trained on. The model acquires the ability to deploy those skills in new ways by interpreting languages and image commands using knowledge gleaned from the web. The model is able to repurpose pick and place skills learned from robot data to place objects near semantically indicated locations. Okay. Such a specific number of icons, despite those cues not being present in the robot data. The model can also interpret relations between the objects to determine which objects to pick and where to place it, despite no such relation being provided in the robot demonstrations. Furthermore, if we augment the commands with chain of thought prompting, the model is able to make even more complex semantic inferences, such as figuring out which object to pick up and which object to drink. Okay, I don't like that they're repeating language. I kind of find that super annoying when a paper has like the same sentence 4 times. They had this sentence earlier. But, okay, what they're describing here is that the actual joint commands are not outside of the distribution. So when they say emergent behaviors, they're talking about kind of semantic understanding. So it's not like the robot is alert, like this robot could not pick a light bulb off the ceiling, right? It couldn't move up and grab a light bulb and twist the light bulb and take it down, because the joint commands for moving up and picking don't exist in the robot data. If you notice, every single one of these examples, the robot is always picking down, and it's something on a table and it's picking down. because that's all of the joint data, all of this robot joint data that they trained it on is all of this like picking down kind of data. So the emergent behavior is only in the kind of vision understanding, where all the data that they fed it is it just kind of like picking things out of a bin kind of randomly. But here they're asking it to do kind of weird, complicated things like, oh, move the banana on top of the flag of Germany, right? So that is something to think about, where it's not like it's generalizing outside of its actions and trajectories. It's only generalizing in terms of the semantic understanding of like where to put the thing and what thing to pick up. But I don't know, that's a little bit less hype. You know, that would have been really cool if it could generalize outside of its actions space. Okay, family of models derived from fine-tuning. Our experiments investigate, here's 55 billion parameters, so there you go, there's the size of the model. Trained on the internet data and instruction annotated robotic trajectories from previous work. So this is the extra data. They're not really going to tell you anything about that, to be honest, because that's going to be proprietary. But a bunch of robot trajectories. Over the course of 6,000 robot evaluations, achieve significant improvements to generalization over objects, scenes, and instructions, but not actions. And exhibit a breadth of emergent capabilities inherited from web-scale vision language pre-training. Okay, related work. So in this related work section, they're basically going to cite every single other DeepMind paper and make sure to increase their citation counts. Several categories, perhaps the two most relevant are representation learning models like CLIP. So everybody knows CLIP. This one is one of the better papers in I would say the last decade, because it's just used everywhere. But basically, the point of CLIP is to create a representation, which is basically a manifold in some latent space where you can project an image into that latent space, and you can also project text into that latent space. So you're learning a representation that includes both language and image. So you can do one-to-one correspondence like that. You can find the closest language to an image. You can find the closest image to some language. You can pick the piece of text that's more relevant to the image, and so on, which learn common embeddings for both modalities. And then vision language models in the form of vision text. This is the VQA, or visual question answering models, that they're going to be using for this model, or this paper. Can you provide fine-tuning code for SAM on custom dataset to detect and count the objects as well as correct the misclassified segments? That's a deep cut, Mishra. So you're referring to, I think we had a couple coding streams on fine-tuning the segment anything model. I think at this point you definitely don't want to use my code for the segment anything model fine-tuning. I think there's a million other people who've implemented way better versions of that and have continued to work on that. So I would go ahead and do that. Go do segment anything fine-tuning. Here you go. Come here onto Encode, and then there you go. You can do whatever this guy's doing. Okay, back to this. Have been used to provide pre-training for a wide variety of applied, such as object classification, detection, segmentation. In this work, we focus on the latter category. These models are generally trained on many different tasks, such as image captioning, VQA, and general language tasks. While prior work studied VLMs for a wide range of problems and settings, including in robotics, our focus is how the capabilities of VLMs can be extended to robotics closed-loop control by endowing them with the ability to predict robot actions. But they can't generalize outside of the robot action space that they were given, leveraging the knowledge already present. Generalization robotic learning. Developing robotic controllers that can broadly succeed is a long-standing goal. A promising approach in robotic manipulation is by learning from large and diverse data sets. By doing so, prior methods have demonstrated how robots can generalize to novel object instances. You have some of the 2017, 2018. This is kind of my era when I was working on robotics at Google. That was like 2016, 2017, kind of that stuff. So I was definitely not doing this kind of stuff. A new goal, language instructions. and unseen environments. Unlike most of these prior works, we aim to develop and study a single model that can generalize to unseen conditions amongst all these axes. A key ingredient is to leverage pre-trained models that have been exposed to data that is much broader than the data seen by the robot. Yeah, basically the internet. The best way for the robot to learn is to read on the internet. Pre-training for robotic manipulation. Pre-training has a long history. Most works focused on pre-trained visual representations. So this was pretty standard pretty much everywhere, right? Where basically it used to be that really only the vision model was deep learning. So in 5 years ago, maybe 10 years ago, you would have robots, right? But only the vision would be using deep learning, and the vision would have some convnet, and that convnet wouldn't even be trained on specifically the robot stuff. It'd be trained on ImageNet. So you would have a convnet or a CNN that's trained on ImageNet, and then you're using it to take your images from the robot and get a visual representation, and then you would use that visual representation to do whatever downstream task you wanted. So that concept of using pre-trained models for robotics is not new, but end-to-end with LLMs, that is definitely new. That can be used to initialize the encoder of the robot's camera operations via supervised ImageNet classification. Damn, look at that. It's like literally on point. Objectives that are tailored towards robotic control. Other works have incorporated pre-trained language models, often either as an instruction encoder. Rather than using pre-training vision models or pre-trained language models, we specifically consider the use of pre-trained vision language models, which provide rich, grounded knowledge about the world. Prior works have studied the use of VLMs for robotics. All of these are relatively recent here. You got 2022, 2022, 2023. Part of the inspiration for this, identifying objects, high-level planning, providing supervision or success detection, clipport and MOO. Here's the paper you referenced, Chris. Integrate pre-trained VLMs into end-to-end visual motor application manipulation policies. Such a fancy way to describe just a robot, you know? Visual motor just basically means a motor commands that are ultimately coming from the vision system. Manipulation is picking, placing, manipulating. So, right, using your hand or the little robot hand to like do things in the real world, separate from locomotion. So, locomotion is more like the Boston Dynamics robots, right? Where basically you're moving in the real world, right? So you're more thinking about where do I put my feet and how do I move around in this real world. Manipulation is using your hand to manipulate stuff. And those have always kind of generally been separate, but now more and more they're becoming one. So manipulation and locomotion are starting to become the same discipline. Both incorporate significant structure into their policy that limits their applicability. Our work does not rely on a restricted 2D action space and does not require a calibrated camera. This is very important too. So camera calibration is a huge pain, and basically what you used to have to do is that the control systems of the robots were based around perception systems, giving them a guess as to the location of things. So basically the perception system would say, this is an apple, I'm going to detect it as an apple, and then I'm going to use stereo, the fact that I have stereo cameras, to basically tell you how far away this apple is, and then I'm going to tell the control system there is an apple at this exact position in 3D space. And because the accuracy of that position in 3D space is extremely important for the control policy, you would basically have to be very careful about camera calibration in order to make sure that your perception system is perfectly calibrated so you get perfect detections and perfect estimates of position. But that's a huge pain, right? That's a huge pain to have to do that. And eventually, if you basically feed everything into an LLM, maybe you don't have to do that. Maybe you don't have to have a calibrated camera. And if we ever want to put these robots in a home, you got to get rid of this camera calibration requirement, right? You got to be able to have a robot where if I bump its head and the camera jiggles inside the housing, where it's not completely fucked, you know. And the only way to do that is basically kind of to do it all end to end, and basically the robot adapts to the fact that the camera is jittered. Moreover, a critical distinction, unlike these works, we leverage VLMs that generate language, and the unified output space of our formulation enables models' weights to be entirely shared across language action tasks. So this is basically just saying that the language and action model is basically the same model, and it has the same weights, right? It has the same parameters that it's learned, and they're shared, which is a fancy way of saying is this the same model. And the unified output space just basically means that the output of this language model, let me go to the actual thing here. The output of this language model is these tokens, and these tokens can basically be text or they can be actions. They're the same. You don't have to have a separate model that outputs actions and a separate model that outputs text tokens. The same model outputs both. Okay. Now we're done with related work, and now let's do vision and language action models. So this is where they're going to describe their method specifically. In this section, we present our model family. So model family means there's a couple different models. I wonder, or maybe they just train different sizes, is my guess. For enabling training to directly perform closed-loop robotic control. Closed loop because the vision creates the action, and the action moves the hand, which then gives you a new vision, so the loop is closed. First, we describe the general architecture of our model and how they can be derived from models that are commonly used for vision language tasks. Then we introduce the recipes and challenges of fine-tuning large VLMs that are pre-trained on web-scale data to directly output robot actions. We describe how to make these models practical for robot tasks, addressing challenges with model size and inference speed. This is something that we were talking about on the stream for the language models are general pattern machines, where one of the biggest problems with putting an LLM inside every single robot is right now it's the model size and inference speed, is that you're going to have to figure out how to make these models very, very small and perform inference very, very quickly, right? If you envision a world where you have a $3,000 robot in your house, right, that's using a language model to do everything, you want to have a language model that fits inside a very small and cheap processor, right? You don't want to have a H100 inside every single robot in your house. Vision language models that we build on take its input one or more images and produce a sequence of tokens, which conventionally represents natural language text. Such models can perform a wide range of visual interpretation and reasoning tasks, from inferring the composition of an image to answering questions about individual objects and their relations to other objects. Right? And it's important to note that they're not a lot previously, when people were doing robotics and they were using pre-trained vision models, they were using pre-trained vision models that were detection models or pose detection models, right? And these type of vision models give you precise answers about this is the exact area, pixels in the image that correspond to a dog, or this is the exact position of someone's face in this image. But these visual question answering models, they don't do that, right? These VQA models, it's not like they're telling you exactly where in the image is the egg, right? The like 6D position of this egg in the image, or the actual joints of this donkey. It just kind of has some idea that it's a donkey, but it doesn't know exactly the position of this donkey, which is separate from the pre-trained vision models that you would normally see used in robotics. We adapt two previously proposed VLMs, PaliX and PalmE. So I think these are both Google papers. Relatively recent too. PalmE, I think, is the language model, and then Pali is the vision VQA. PaliX. Yeah, PaliX is the VQA model, and then PalmE is just a LLM. We refer to the vision language action versions as RT-2 PaliX and RT-2 PalmE. Okay, so they're basically training two variants of these. We leverage instantiations of these models that range in size from billions to tens of billions. Okay, so this is where the model family is going to come in, where basically they're going to try to see if scale matters here, right? Can you do this with a very tiny model, or do you need the big models, right? If you can do it with a tiny model, that's a huge benefit, because then it means that we're close to releasing this as a product. But if it kind of only works with the really big, the 70 billion Llama 2 model, then we are going to have to wait a little bit longer for GPUs to get cheaper and smaller, or for quantization and inference tricks to get better and better. Okay, we got pick up the bag, move the apple to the Denver Nuggets. Put strawberry into the bowl. Pick land animal. Move Coke can to X. So all the examples here are basically showing you that the task can have very nuanced and semantic concepts, right? Like move the Coke can to Taylor Swift, and you have pictures of celebrities here. Like the robot understands which celebrity is Taylor Swift. Like that is the type of generalist knowledge that they're putting into these robots. Thank you, Kalina. But the robot is not able to generalize to. It's not like, for example, like the example that I said, right? It's not able to unscrew a light bulb because that's outside of its action space, but it's able to recognize celebrities. So that kind of gives you the idea how the generalization that they're referring to is more in the semantic kind of reasoning and visual understanding space, not necessarily in the action and joint and control space of the robot. To enable vision language models to control, they must be trained to output actions. We take a direct approach representing actions as tokens in the model's output, which are treated in the same way as language tokens. We base our action encoding, so this is the tokenization of the actions, on the discretization of the RT-1 model. The action space consists of a 6-DOF positional and rotational displacement. So this is where I feel like they could have done quaternions. I feel like they should have made this 7-DOF. They should have done X, Y, Z, and then they should have also done the quaternion instead. So I'm a huge fan of these quaternions, and these are super cool to learn about. But quaternions are basically 4 numbers that represent a rotation. And you have, this is Euler angle, so you have roll, yaw, and pitch. But quaternions are 4 numbers. And they're cooler too, because I think you can basically interpolate in quaternion space, and it has a different meaning than interpolating in Euler space. And I think that if we actually could look at the math of the universe that's running the simulation, I think it's in quaternions. And you can add quaternions, you can multiply quaternions, things like that. It's actually a much better representation of rotation, I think. As well as the level of extension of the robot gripper and special discrete command for terminating the episode. So they have 6D for the position, then they have the gripper command, and then they have a end episode command. So 8 numbers is the action space. The continuous dimensions are discretized into 256 bin uniformly. So 256 possible positions. So for every single one of these Euler angles, right, that's 360 degrees, but they're not discretizing it into 1 degree increments. They're discretizing it into 256 bins. So there's a little bit of, you're going to run into discretization issues here. I feel like ideally, you would want this to be continuous, but the problem is then because they're turning it into text, that's where this 256 is coming from, right? That number is so that it fits in a specific number of bytes, right? So they want to fit it inside a specific integer data type, so that's why they discretize it into this 256. Anytime you see a number like that, 2, 4, 6, 8, 12, or 16, 128, 256, those numbers are not random, right? Those powers of 2 mean that they're fitting it in some specific number of bytes. In order to use these discretized actions to fine-tune a vision language and vision language action model, we need to associate tokens from the model's existing tokenization with the discrete action bins. This requires reserving 256 tokens to serve as action tokens. Which tokens to choose depends on the particular tokenization used by each VLM. So kind of what they're discussing here is that The tokenization used for this pre-trained vision language model is a fixed dictionary, right? There's a specific dictionary that was used with all possible tokens for that. So they have to pick basically weird characters, or they have to add to that dictionary. So let's see what they're going to do here. In order to define a target, we can convert an action vector into a single by simply concatenating action tokens for each dimension with a space character. This is something that we saw in the other paper as well, where basically some of these language models, they break up numbers such as 128 into 3 tokens. So the Llama 2 model does this, where it doesn't see the number 128 as a single token. It sees it as 3 tokens. It sees it as 1 token, 2 token, 3, or token 8. So basically 3 tokens. But if you don't have a model that breaks up numbers into each individual token, you basically have to put these spaces in here, because or else it'll get confused and it'll just read this entire thing as one number, as one token. So here you have the terminate command, which is going to be a 1 or a 0. You have your 3 different X, Y, Z deltas. You have your rotation deltas, and then you have your gripper extension. The gripper extension being 127 is kind of weird. What is that number? I would have thought the gripper would have been 0 to 1 as well, or I guess maybe they're controlling the exact distance in the gripper. What does the 4th position mean in quaternion? So don't think of it as the first 3 numbers in the quaternion mean the 3 Euler angles. It's literally the 4 numbers together mean one representation. And so it's not like the first number means the yaw, second number means the pitch, and third number means the roll, and then the other one flip. It's like all 4 of those numbers together represent a rotation, or a position. And the guy who actually came up with it, yeah, this is kind of a crazy story, but like the guy who came up with this in like 1843, he discovered it in a flash of genius, aka the aliens gave it to him in his brain, and he wrote it on a bridge. So, kind of crazy story. Boo boo. Did you guys hear her? Boo, come here. Say hi to the stream. Come here. Come here. Here we go. Here's the kitty. You have been blessed by Petit Boo. Okay. Okay, Petit Boo. Okay. Control W. Control 1. For the PalmE model, which does this convenient representation of numbers, integers up to 1000 have a unique token. Okay, so I guess PaliX is like Llama 2, where it does break up integers into unique tokens. We simply overwrite the 256 least frequency used tokens. Okay, so they're not going to add to the token dictionary. What they're going to do instead is find the weirdest tokens, which are probably like weird special ASCII characters that no one knows, right? Like an umlaut on an O or something like that, right? Like umlaut O, right? Like this, you know, that the token that represents whatever the fuck this letter is, maybe with like a weird Chinese character, maybe something like that, or like some weird character in a different language. But basically, the least frequently used tokens are just going to overwrite those. Form of symbol tuning, which has been shown to work well for VLMs in prior. So here what they mean by symbol tuning is just fine tuning, where you're overwriting some of the symbol tuning. And the reason that works is because of catastrophic forgetting, right? Take the action representation. O is a common letter. Okay, so maybe not that. Maybe something weird. Taking the action representation described above, we convert our robot data to be suitable for VLM model fine tuning, where our inputs include robot camera images and textual data description using standard VQA format. What action should the robot take to task instruction A? So basically, they're going to convert their existing robot data, right? They just have thousands of these pick and place trajectories, and they're going to convert it into this VQA format so that they can fine tune the already trained VLM, which is PaliX, and then fine tune it on this extra robot data. And they need to basically convert the robot data by using these least frequently used tokens. Actually, I'm kind of curious. What are some low, rarely used text tokens in LLM tokenizers. God, dude, like these LLMs are starting to become like unusable. Like they're so safe that it's like I can't even get an answer from them half the time. All right. Modern text data tokens representing Old English words like thee, thou, prithee. Rare Unicode symbols such as chess, rook, or pi are likely used. Specific punctuation such as interrobangs, pilcrow. I've never even seen this. What the fuck is a pilcrow? And then section signs. Rare emojis. Oh, emojis. Most of these tokenizers have emojis. Oh shit, dude. They could probably use emojis. Diacritics such as accents and umlauts. This was my guess, but I think you're right, Shovel Pile, that there's probably a ton of like German training data where those tokens are used all the time. So I do not actually have detail. I'm harmless and helpful and honest. All right, you are useless. Perhaps we could have a more constructive conversation. I think so. Okay, co-fine-tuning. As we will show in our experiments, a key technical detail of the training recipe is co-fine-tuning robotics data with the original web data instead of naive fine-tuning on data only. Okay, so what do they mean here? We notice that co-fine-tuning leads to a more generalizable object since the policies are exposed to both abstract visual concepts and low-level robot actions during fine-tuning instead of just robot actions. During co-fine-tuning, we balance the ratios of robot and web data in each training batch by increasing the sampling weight on the robot data set. Okay, so what the fuck does this mean? It means that, let's say you have 2 data sets. If you train only on data set A, and then you train only on data set B, that's going to be a different result than if you train on dataset A and dataset B at the same time, right? Like every single batch of data that you're feeding to the model has a little bit of A and a little bit of B, right? If you only do A and then only do B, you're basically going to forget A. Anything that was useful to succeed in A is probably not going to be useful to succeed in B, so the language model will kind of just forget that, right? The deep learning model will just start to forget what it learned in A. That's the catastrophic forgetting problem. So what they're saying is they're calling this co-fine-tuning, where they want to fine-tune on this robot data, but if they just fed only robot data to this PaliX model, the PaliX model will just start to get really shitty at what it did before, and they don't want to lose that. They don't want to lose the intelligence that was already there in the PaliX. So what they're going to be doing is for every training batch that they're going to be using in this fine-tuning, they're going to start with just a little bit of robot data. So it's like 90% VQA data and then 10% robot data. And then they start doing a little bit more and then a little bit more and then a little bit more. The sampling weight here refers to the fact that when you're creating a batch of training data, you're sampling from a data set, and the sampling, you can put weights in front of those. So specific things are sampled more frequently than other things. There's a bigger weight to sampling it, right? So the weight there doesn't mean like the weight inside a neural net. It means like it means like a number, like a hyperparameter that you pick that's saying how much more likely am I to pick robot data than just generic VQA data. So they're being tricky about the fine-tuning here. They're being mindful not to overwrite what the PaliX model has learned. Okay. Output constraint. One important distinction between RT-2 and standard VLMs is that RT-2 is required to output valid action tokens for execution on the real robot. Thus, to ensure that... Jesus Christ, I got cat hair in my nose and now it's impossible. To ensure that RT-2 outputs valid action tokens during decoding, we constrain its output vocabulary via only sampling valid action tokens when the model is prompted with a robot action task, whereas the model is still allowed to output full range of natural language tokens on standard vision language tasks. Okay, so they have basically an extra constraint on the robot where I think that's what we saw here. Let me see if I can get the picture. But yeah, you see, so they give it the question answer, but then they give it this task token here. So there's basically a token that tells it whether it's doing normal vision question answering or whether it's doing specifically robotic actions. So unless this task token is there, they don't, they're not going to feed these tokens into the robot. I guess that's probably a good, like, kind of like a safety thing too, because you wouldn't want the robot to accidentally move if there's like an emoji in the output. Okay, the size of modern VLMs can reach tens or hundreds of billions of parameters. The largest model trained in this work uses 55 billion parameters. I wonder whether this includes all the models. This is something that we saw in the meta transformer stream, is that they were kind of being misleading, and they were saying the parameter size but only counting part of the model. So whenever they say 55 billion, does that include this vision transformer? Does that include the language model, or is it just both of these? So I don't know. We'll see what exactly that means. It isn't feasible to directly run such models on the standard desktop style machines or on robot GPUs commonly used for real-time robotic control. Yeah, it's a huge problem right now, but I think we can solve this. I think that there's so much money in GPUs and edge computing that I feel like we're just a couple years away from being able to run 70 billion parameter Llama 2 model on like a cell phone. I know that sounds crazy to say, but I feel like there's so much money and so much incentive, and cell phones are kind of the perfect carrot at the end of the perfect carrot to kind of get us to a point where we can basically do real-time LLM inference on something like a cell phone. And if you can do real-time LLM inference on something like a cell phone, that means you can do real-time LLM robotic control. By over an order of magnitude to be used to closed-loop robotic control, and therefore requires a new set of solutions to enable efficient real-time inference. We develop a protocol that allows us to run RT-2 models on robots by deploying them in a multi-TPU cloud service. Okay, so what does this mean? So a cloud service is a service, which basically means something that sits there and waits, and then you ask it to do something and it gives you an answer, so it serves you, right? Most applications, most kind of like products or software systems are kind of designed in this server client kind of architecture where you have something that's running that's the server, right? It's providing service, and that thing is usually running in the cloud. And the multi-TPU, the TPU is the tensor processing unit. It's basically, you could think of it as TPU Google. You could think of it as Google's GPU. So Google makes their own GPUs, and they're called TPUs, right? That's a genius marketing move. Rather than calling it GGPU, they could have called it GGPU, and then nobody would have remembered it. But by calling it a TPU, now everybody instantly recognizes that as Google's TPUs. But these TPUs actually very rarely are in a single. There's very rarely do you see a single TPU. Almost always they're in these pods. And here you have 4 TPUs. This is a TPU v4 pod, right? So there's 4 of those pods, and the v4 is actually the version, maybe not the number of pods or TPUs. I'm not exactly sure. I think this is maybe version 4, or yeah, actually TPU v4 with 4 TPUs on it. So basically, they have one of these pods in the cloud, and that is acting as the service, querying this service over the network. And this is actually, I've done this as well. So I did this for, I made a little, what do you call it? I think I called it, I forget what I called it, but basically, if I go into my channel, and I go into the speech-to-speech AI conversation app. So when I built this, this is running all in the cloud. So it's all doing it through cloud services, where basically no compute is actually running on this locally. There's no model inference running locally. It's all just sending a request to some cloud service, which provides the answer. So all of the text-to-speech, speech-to-text, all of that is happening not on this computer, which means that I could run this on like a Raspberry Pi. And they're basically going to be doing the same thing, where this is called cloud robotics. And there's a lot of people who think that maybe the answer to robotics and the computational power that's required is that you don't actually have anything running on the robot. It's all running in the cloud. And that might actually be the way to do things, because if everything runs in the cloud, then they can also control it, right? So then not only is every single robot cheaper, but then also all the inference is done in the cloud. The model is never on your robot, so you could never shut off the robot and then take the chip out and then actually measure and see what the model parameters were, right? So I think that there's a couple different reasons why we might see a world in which everything is done as a cloud service, especially robotics, and we have this kind of cloud robotics. Okay, the largest model we evaluated is 55 billion parameters and can run at a frequency of 1 to 3 hertz. So hertz is per second, so 1 to 3 hertz means basically 1 to 3 times per second. The smaller version of that model, consisting of 5 billion parameters, can run at a frequency of around 5 hertz. Okay, so interesting here is that 55 billion runs at 3 hertz, 5 billion runs at 5 hertz. So there is still a latency issue here, right? So part of when you put everything in the cloud like that, you have to deal with the kind of latency and the messaging overhead. And it seems like basically the messaging overhead is preventing this from going way lower, right? This is an order of magnitude of 10 in the model parameter size, but just a order of 2 on the control frequency. So that's telling you that the messaging and the overhead and the latency and stuff like that is still an issue. Okay, I'm kind of getting carried away. This last paragraph here took way too long. Our experiments focus on real-world generalization and emergent capabilities of RT-2 and aim to answer the following questions. How does RT-2 perform on scene tasks and generalize over new objects, backgrounds, and environments? Can we observe and measure any emergent capabilities? What does the generalization vary with parameter count and other design decisions? And can RT-2 exhibit signs of chain-of-thought reasoning similar to vision language models? Unless specified, we use a 7DOF mobile manipulator. So 7DOF is 7 degrees of freedom. It just basically means that this arm has 7 joints in it. Right? You have one there, you have one there, you have one there. So there's 7 joints. And then mobile, because it's on a mobile base, right? It's a manipulator, but it's not just sitting glued to a table. It's on a little mobile base, so it can move around. We also demonstrate examples on the project website. We train 2 instantiations, the RT-2 PaliX and then the RT-2 PalmE. We leverage the original web scale data, which consists of VQA, unstructured interwoven images and text. We combine it with robot demonstration data, which was collected with 13 robots over 17 months in an office kitchen environment. Okay, but how much data is that? Each robot trajectory is annotated with a natural language instruction that describes the task, such as pick, open, place, and so on. For all RT-2 training runs, we adopt the hyperparameters from the original PaliX and PalmE papers, including learning rate schedules and regularizations. So they're not really messing with any of the training configs for PaliX and PalmE. They're really just kind of adding this extra data and then training a little bit more on it. We compare our method to multiple state-of-the-art baselines that challenge different aspects of our method. All of the baselines use the exact same robotic data. To compare against a state-of-the-art policy, they compare to RT-1, so it's difficult to have a baseline when you're doing something that's so unique and so weird that there isn't like a bunch of baselines and benchmarks to compare against, so really they're just going to be comparing to their own previous work, which is RT-1, but you know, the flip side to that is that, of course, you're going to be better than RT-1 because this is RT-2, right? So, I don't know, it's hard to compare. We use VC1 and R3M. These are policies implemented by training a RT1 backbone to take the representation as input. To compare against other architectures using VLMs, we use MOO, which uses a VLM to create an additional image channel for a semantic map, which is then fed into an RT1 backbone. Okay, so these kind of seems like older approaches here that are based on kind of this more modular vision separate from control strategy. Unseen objects, unseen backgrounds, unseen environments. So here they're changing the background of the table. You see here you got the wood texture, you got sky texture, you got weird leaf texture. Unseen environments, so kitchen sink, office chair. Unseen objects, you got weird things like a pear and a Scoopy looking thing. To evaluate in-distribution performance as well as generalization or out-of-distribution performance, we compare to 4 baselines, which include over 200 tasks. 36 for picking, 36 knocking, 35 placing, 48 moving, 18 opening and closing, and 36 picking and placing out of drawers. So these are all the different tasks. And it's kind of, I feel like this is still a very limited distribution. That's one thing to note here, is that all of these are kind of just like a variant of a pick, right? Like how much different is a picking out of a drawer than picking off a table, and how much different is placing than picking? And all of these are largely kind of the same distribution of behaviors, right? I feel like I would have liked to see this paper, but with a much more varied distribution of behaviors, such as like grabbing a ball out of the air, or like painting or something like that. You know, there's so many interesting behaviors and tasks that you could do with a gripper and a hand that I feel like we're still limited in this kind of, we're still stuck in this like pick and place kind of mindset. And I feel like we don't necessarily need to be. I think we can go beyond that. Split into unseen categories, and additionally split into easy and hard cases. For unseen backgrounds, hard cases include more varied backgrounds and novel objects. Lastly, for unseen environments, hard cases correspond to more visually distinct environments. Okay, so R3M, VC, this is all the different things that they're comparing to. Here you have the 2 different versions of RT-2, starting from either PalmE or PaliX. And you have performance, I guess, in success rate. So each of these tasks consists of basically one episode, which is basically just one, like kind of like a 5-10 second duration where the robot is like, all right, do the thing. And it does the thing and then it ends. So you can see here that RT2 is succeeding roughly 75% of the time. Gets a little bit lower whenever it can't see, whenever it's on things that are outside of the distribution. These unseen backgrounds, unseen environments, gets a little bit lower, more like 50% of the time it succeeds. But compared to these previous methods, which are kind of hovering around 25%, that's huge, right? And the important thing to realize here too is that these previous baselines, like RT1, does very well in this environment here, right? Look at that. It's about the same. It's about this 90% pick rate. But as soon as you go somewhere that it hasn't seen, as soon as you change the background, it goes down to 40%. And that's, when I was doing robotics, that was basically, that was the state that we were at, where you would see a paper that said 96% pick accuracy. And then you change the color of the table from wood grain to like this sky grain, and the accuracy goes down to like 10%, right? So that just always felt terrible. I felt kind of gross, like publishing papers where people would argue things like that, and it's like, dude, it's like so fragile to everything. But now we're starting to see this ability to generalize, although I still feel like it's a little bit, this is still pretty close to the original distribution. I would like to see generalizations that are way out there. Yeah, Kalina, interesting to see if the model generalizes beyond its 200 task set. Agreed. Here on average, perform similarly, perform better, blah, 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 harder versions of generalization while underperforming, resulting in a similar average performance. You are very loud, Boo. Can you guys hear her? She is so loud. To provide an additional point of comparison using open source baselines, we leverage the open source language table simulation environment. Yeah, so evaluating robots in the real world is a pain. It takes a bunch of time. You have to have someone sitting there. It's not fun. But simulations, it's way easier to do, right? You could have hundreds of episodes just running on a server somewhere. So here they're using a language table simulation environment, and then they're basically just evaluating all these different models in that simulation environment. We discretize and encode actions in text. Okay, represent 2D Cartesian deltas. The resulting model can run an inference at similar rate and as other baselines. results are presented. We observed that the performance boosts, indicating that the VLM-based pre-training together with expressive can be beneficial in other scenarios. We also show qualitative real-world out-of-distribution behaviors. There's a little typo here. Type the word behavior twice. Demonstrating novel pushing tasks and targeting objects not before seen in this environment. Maybe she's hungry. Generally, the kitty doesn't eat, but yeah, she eats a little bit later in the day. But usually it's not food, it's actually play. She doesn't have a very high food drive, but she has a very high play drive. So she really loves play. So if no one's playing with her, she's like, why the fuck is no one playing with me? In addition to evaluating the generalization capabilities, we also aim to evaluate which degree such models can enable new capabilities. Okay, so this is the language table simulation environment, which I think is basically just you're pushing little things around. So push the ketchup to the blue cube, push the blue cube to the Tabasco. And right, the impressive thing here is not that it's actually pushing towards that, because it has plenty of robot trajectories that do that. The impressive thing here is that it knows what Tabasco means, and it knows what ketchup means, right? The fact that it can just generalize to weird objects like that that's the impressive part. Transferring knowledge from their web, aka emergent. Play with me, human. Yeah, that's basically what she's saying. We do not expect such transfer to enable new robotic motions. All right. Yeah, so this is kind of what I was saying this entire time. This is kind of like, to me, the only negative of this paper is that it's really not allowing any new motions. It's really just semantic and visual concepts. Transferred, we demonstrate some examples of such interactions. We find through our explorations that RT-2 inherits novel capabilities and basic reasoning. Right, because LLMs have basic reasoning, so it basically has these abilities now. Pick up the bag, physical understanding to disambiguate between the bags and recognize the precariously placed object. So this is what they're talking about here, where they can say, pick up the bag that's about to fall off the table. Where is it? I feel like I saw the picture of that. Oh, here we go. Here's a little robot. So 2 times speed. So this is at 2x speed. You can just see how slow it is. You see that? And then actually right here, you see how this power cable comes here. So there's a little power cable and then there's a little Ethernet. So basically this robot is running by itself, but you could actually, if you needed to charge it, you would plug it in here, and then if you wanted to connect to it with your computer, you would plug into this Ethernet cable here. So those are the two things there, and I think they actually got it to the point where it could actually plug in itself, which is kind of cool. Here you have a not a structured light sensor, laser sensor, which is basically it's sending out little lasers and it's spinning, and then it's basically giving you a 3D point cloud. But honestly, this type of shit is pointless now. You don't actually need these laser sensors anymore. I think because of LLMs and because of all the pre-training on internet scale data, I think you're actually going to see this go away, and we're going to get rid of these sensors, which are adding extra cost to the robot, and you're just going to only see cameras. And another thing you want to notice here is notice how this robot has a ton of scratches. You want to see that. If you're looking at a video of a robot and the robot looks pristine, something's fishy, right? Because a pristine robot means that no one's ever used that robot. That means that robot sits still 99% of the time, and then when the investors come in, they have it do its one thing, and then that's it. You want to see scratches on a robot. You want to see a robot that looks like it's been used, and it looks like it's picked hundreds of thousands of things. So when I see this robot and it's got all these scratches on it, that makes me happy. That makes me think that this robot has lived a good life. You know, it's been used a lot. It's still kind of a shitty pick on that cup. You know, really it should pick it like that horizontally. It's also extremely slow. Like all of these videos are sped up. Okay. Take 2 baselines. Reduce the variance of these experiments. I don't know if you want to reduce the variance of these experiments. All 4 models are evaluated one after another in the exact same condition. So kind of what they're referring to here is that it can be sensitive to the lighting. So if you evaluate one model in the morning and then a different model at night, it's going to be difficult to know whether or not it was because the morning or the night or the lighting or maybe something else impacted it. So by interweaving the evaluations of one model and the other model, it basically reduces the possible effect of external variables. Kind of seems like they're doing everything at night. You seen this? You seen all the darkness here? So either they turned off the lights or like all of this was done at night. Something weird. Got to set up RT-2 to play with Kitty. Believe it or not, I actually have a setup kind of like that. I have, I'll show it to you. Actually, I might do a stream on it, but I basically have 2 servos with a little cat toy on it, and I want to do something like this. I want to basically have a language model output the actions for it. But last time I got it, I had basically a camera that would detect a cat, and then if there's a cat, it would move it. But the Boo, which is the cat, is too smart, and she knows that if you're not holding the toy, she's like, I don't give a fuck. So she's too clever to be played with by a robot. Okay, so here they're just kind of describing multilingual understanding, so it basically instantly understands different languages. Human recognition, move the Coke can, demonstrate human-centric understanding and recognition. Yeah, you get all these free emergent abilities. Our VLA models significantly outperform the baselines. We also note that while the larger PaliX-based model results in better symbol understanding, reasoning, and person recognition, the smaller PalmE-based model has an edge on tasks that involve math reasoning. That's kind of cool. So there's a slight difference between the PaliX and the PalmE. More capable at math calculation than the mostly visually trained PaliX. Huh. That's kind of cool. Symbol understanding, reasoning, human recognition. Oh shit, this is actually awesome. Look at this. I've never seen this chart before. It's a bar chart, but the bars are shown for multiple model sizes. So the full green bar is the 55 billion parameter size model, and then this smaller gray bar that is inset is the 5 billion parameter model. That's a really cool visualization. I've never seen that. I'm going to totally steal that. Okay, but here you have fine-tuned, co-fine-tuned, which is when they're doing that like interleaving, and then from scratch. So you can see how the co-fine-tuned versus fine-tuned, it's actually not that much of a difference, just a little bit of a difference there. But from scratch is basically garbage. If you just take PaliX and then just train it only on robot data, it just is garbage, performs like nothing here. New benchmark for state-of-the-art robotics. Entertain Boo. Is it Boo? It's actually Boo, like this. Noki Bengal Kitty Instagram. She does have an Instagram. Noki the cat? Is it this one? No, it's not this one. That's a different cat. Okay, it's actually called booboo.jpg. I don't know. I don't even have an Instagram, so I don't know what the fuck I'm doing on Instagram. Let me see. I'm not finding any of this. Baboo JPEG Instagram. Alright, I can't find it. I'll post it on the channel later. Wait, I'm getting sent. I'm getting it sent. You guys need to see this? Alright. Booboo.jpg. I feel like that's what I typed. Sorry, guys. I'm sorry for those that are actually trying to booboo.jpg like that. It literally doesn't show up. Here we go. This is it. This is the channel. Here you go. All right, guys. This is Babu. This is back in San Francisco, back when I was living there. All right, and then Instagram locks you out. Okay, back to some robots. Sorry about that. Can RT-2 exhibit signs of chain of thought reasoning similar to vision language models? That's the most cattish cat name I've ever heard. Yeah, she's quite the little drama queen for sure. She knows how, she's like super clever. Look at, this one's actually super great. Or not this one, this one. She knows how to climb, or how to, let's get the link to this. Open link in new tab. She knows how to open doors. See that? Wait a second. Very smart little cat. She can open the doors. AGI right there, yeah. So like when I do my streams, I'll close the door, but she just opens the door and comes in, you know. Okay. Fine-tune a variant of RT-2 with PalmE for just a few hundred gradient steps to increase the capability of utilizing language and actions jointly. So, I mean, a few hundred gradient steps doesn't necessarily mean anything, because it's like, what's the learning rate that you're using for these gradient steps? If you're taking a few hundred gradient steps with a huge learning rate, you could end up very far. But if you're using a very tiny learning rate, then yes, it's not a lot. We augment the data to include an additional plan step, which describes the purpose of the action the robot is about to take, followed by the actual action. Okay, so basically they're going to do an extra step here. They're going to say, instruction, I'm hungry, plan, pick chocolate, action, this. So here, instead of Q and A, there's going to be Q and then P for plan and then A. And I guess some random human just came up with this pick RX bar chocolate. This data augmentation scheme acts as a bridge between VQA and manipulation datasets. I don't know if I would call that data augmentation. I would call that just larger context. We qualitatively observe that RT-2 with chain of thought reasoning is able to answer more sophisticated commands due to the fact that it's given a place to plan its actions in natural language first. Yeah, so this is the in-context chain of thought reasoning that pretty much works in all kinds of different things. It works for math problems, it works for coding, it works for robots. Provides some initial evidence that using LLMs or VLMs as planners can be combined with low-level policies on a single VLA model. Rollouts, which is just a fancy way of saying episodes or particular instances of one, like an inference. Basically, this is one rollout here. Rollout comes from basically kind of a archaic reinforcement learning term where you would basically roll out all the steps and actions that you took, right? And I kind of find it annoying that even though we're dealing with LLMs and robots, we're still using terminology from reinforcement learning. I think that makes it more confusing, and we should just stop doing that. But I don't know, reinforcement learning people got a reinforcement learning. All right, so here's the extra plan step that they're putting in here when they're fine-tuning, and it does seem to help. Even though RT-2 exhibits promising generalization, there are multiple limitations. Although we show that including web-scale pre-training data boosts generalization over semantic and visual concepts, the robot does not acquire any new ability to perform new motions. Yeah, this is kind of what we inferred. The model's physical skills are still limited to the distributions of skills seen in the robot data, so it's not able to generalize outside of these kind of pick-and-place variants. This is a result of the dataset not being varied enough along the areas of skills. An exciting direction is to study how new skills should be acquired, such as videos of humans. Yeah, this is where you got to take it next. You got to pre-train it on kind of like motion libraries of pose data, right? There is a bunch of data. There is like a motion pose data set. Pose estimation. There's like whole data sets of basically like something like this, humans 3.6M, of like people performing all kinds of weird actions, you know, like pick up a thing, or can I look? Video presentation? Data? Why does this look like it was made in like 1997? Holy shit. But imagine pre-training on that kind of corpus. I feel like we're so close. I don't know, IMO robots in your house in 5 years. Computation cost of these models is high, and as these methods are applied to settings that demand high frequency control, real-time inference may become a major bottleneck. An exciting direction is to explore quantization and distillation techniques that might enable such models to run at higher rates or on lower cost hardware. Or you just do it all through the cloud, right? Because also the internet speed is also increasing. So latency is only going to get better and better over time, right? We're going to have 5G and then 6G and then 7G. And at some point, it's going to be so fast and you can send basically massive amounts of data almost instantaneously. So maybe we don't need to actually run these models on your device. Maybe your device becomes very stupid and actually all the inference is done in the cloud on a giant GPU, and we just have such good satellite internet that it kind of instantly communicates. And the proprietary ones will open up their fine-tuning APIs. More open source models will become available? This is a Google paper. What the fuck are you guys talking about? This is kind of weird. You have a bunch of people working at Google and DeepMind saying they wish that there was more open source models. So this is interesting. That means that this is actually super interesting, because what this means is that this team of people here, right, who are all machine learning researchers, are believers in open source. And I know some of these people. I know this guy. I know Carol. I know Monse. I know some of these people. Like, it's interesting. These people probably believe in open source, but there's like a faction in Google that's probably the like AI safety team, which is more kind of like legal people, and they're trying to like lock it all down, right? They want that regulatory capture. So it's interesting how the regulatory capture kind of like AI safety lawyers, they probably read this paper and approved it. But what this tells me, this sentence here, is that they didn't read it to the end, because this sentence went through, right? If I was some lawyer type person on the AI safety team, I would not let them put, "We hope that more open source models will become available," in a Google DeepMind paper. I would have gotten them to take that line out. So it's kind of interesting here how you have a little bit of rebellion from the researchers in Google against the fact that all of the Google models are all closed source. So I don't know. Language is a good prior to understand and plan actions in the world. Yeah, this language is more, I would say, the paper that we read previously. The language models are general pattern machines. This one is more specifically vision language, so more vision question answering, so the combination of language and vision. But yes, I would say language is kind of the best prior for the real world. We presented two instantiations, PalmE and PaliX, which they're calling RT-2 PalmE and RT-2 PaliX. These models are co-fine-tuned with the robotic trajectory data to output robot actions, which are presented as text tokens. We showed that our approach results in a very performant robot policies, and more important, leads to significantly better generalization performance and emergent capabilities only in semantic understanding and visual understanding, though. It's not emergent capabilities in actual control and robot joints space. We believe that this simple and general approach shows a promise of robotics directly benefiting from better vision language models, which puts the field of robot learning in a strategic position to further improve with advancements in other fields. Yeah, I think it's huge. I think, like, I'm very excited by this field because it just feels like we finally have the answer, right? For so many years, like robotics was just, it just never worked. It was just always trash. The models were trash. The robots were trash. And now we're finally at a point where we just solved it. Like we finally gave robotics the intelligence that they need, and we're so close. Like I think we're literally definitely less than 10 years, but I would say less than 5 years away from robots that you can talk to. You can talk to the robot and say, hey, can you fold the laundry? And it can fold the laundry. And you can say, hey, can you pick up those dishes over there? And it can do that for you. So we are very, very close. Okay, so let's go into the appendices here. You got baselines, some evaluation details, symbol understanding. So does it understand these different symbols? Celebrities, the fact that it can understand celebrities is fucking crazy. It can not move the Coke can to the person with glasses. Like, look at that. That's some next level understanding there. Pushing around. Additional chain of thought reasoning. I wonder if we need continuous learning to really crack autonomous robotics. Maybe that would help with the embodiment problem and stuff. I don't know. I think that, yes, once you have a bunch of robots in the home, you'll want to have some kind of continuous or lifelong learning kind of situation where it is learning from the data that it's collecting, that is being sent back, that is being used to update the model, and then the robot every single day gets a little bit smarter. But I think at some point, the cumulative intelligence of the robot is good enough that you don't need to do any more kind of continuous learning or lifelong learning, as they call it sometimes, where basically the model itself is just so good that it doesn't really need to get any additional data. And I think that if you start thinking about privacy and like, is the robot in your house recording all that stuff? Is the robot that is folding your laundry, does it send the picture of your underwear to Google? Like, I don't know. I think there's unanswered questions there. And to me, the fact that these LLMs and VQA vision language models are actually doing pretty good means that maybe we don't necessarily need to like be pushing gradients from your house, or that would be federated learning, but we don't need to be sending data in kind of a lifelong learning manner where you're kind of accumulating data over the life of the robot. Okay, so here's all the different objects. Oreos, Red Bull cans, green cups, pickle snacks. Cool. We did it, guys. That's all. 26 pages. Also another typo right here. Or not a typo, this is a formatting mistake. Let me drink some yerba mate and then let's summarize this paper. All right. Isn't the challenge of such a robot similar to the one in self-driving? As far as I understand, they use RL in a simulated environment. I think there's different challenges with this type of robot and driving robots. I think the biggest one for self-driving and autonomous vehicles is the safety, right? Is that this robot is so small, so tiny, and it's moving so slowly that it's never going to hurt you. So you don't need to worry about that whole set of things versus like autonomous vehicles. Like, they're moving quickly. It's a giant metal machine like that. The fact that it can very easily kill someone is such a huge challenge that everything needs to be different, right? One of the reasons why they don't do end-to-end learning in autonomous vehicles is because end-to-end learning is kind of a black box, right? You don't know what's going to come out. You don't know what type of action it's going to take, right? And because you don't know what action it's going to take, that means it can't pass certain kind of legal requirements, right? So there's the safety ends up becoming a huge barrier for preventing end-to-end systems in autonomous vehicles versus on a robot. You don't really know what action it's going to take, but because you can guarantee that every action it takes, it's not going to kill you, then you can do end-to-end learning on a robot system. Do I think that there will be end-to-end learning or end-to-end systems in autonomous vehicles 10 years from now? Yes, I think that 10 years from now, what's running your autonomous vehicle will be an LLM, and it'll be doing end-to-end similar to these robots. But You think you could just do it in context? I think the meaning of in context will kind of change. I think that by the time this particular strategy goes into autonomous vehicles, it's like, it's going to be weird, right? It's not going to be doing in-context learning in the way that we think about it as an LLM. There's probably going to be like weird buffers that store kind of intermediate representations than access, like, because the real-time requirement for cars is also much higher, right? Here, you can run this robot at 5 hertz. That's totally fine if it's picking up a banana, but if you're driving 80 miles an hour, you can't. It's got to be like hundreds of hertz, thousands of hertz. You know, you can't be slow at all. Dive to McDonald's fast, please. Yeah, I think we'll get, actually, here's a spicy take, and I actually think it's true. We'll get robots in our home. We'll get autonomous home robots before we get autonomous vehicles. How about that spicy take? Because autonomous vehicles are just stuck in this kind of like 2015 kind of modular, like separate control stack, separate vision stack, separate perception stack, separate safety stack, like all these little modular pieces that all have to basically be tested separately and all have to have safety guarantees separately. They're still stuck in that pattern. Versus I feel like robots, especially these little home robots now, we're just going to leapfrog that. You know, we're already just going straight to LLMs are inside and doing everything end to end. So that's my spicy take, is that we're going to have home robots before we have autonomous vehicles. Okay, I was going to summarize this though. All right, let me summarize this here. But basically today we read RT-2, which is a Robotic Transformer 2, which is a vision language action model. So this is a end-to-end robotic deep learning system on a mobile manipulator, so a robot that has an arm and a RGB cameras. Basically what they're doing is they're fine-tuning a vision question answering model, PalmE 2, or PalmE, or not PalmE, what is it? PalmX, and then Fuck, I forget these. Where is it? Yeah, PalmE and PaliX. So these are basically vision question answering models. They have a separate transformer that consumes the text, and then they have a vision transformer that consumes the image, turns it into tokens that are then fed into a model that can basically answer questions on that. So yeah, they fine-tune this on a bunch of additional robotic trajectory data that is formatted specifically to fit this. They are using a bunch of the low-frequency tokens and overriding those, and some of those tokens basically now represent robot actions, which are basically just XYZ, rotation, gripper, and then end episode. And they're running this on a multi-TPU cloud service at about 5 hertz. There's 2 different sizes. They try 55 billion parameters and 5 billion parameters, and it seems to work pretty well. It can generalize very well to semantic and visual weirdness, right? So you can ask it to do weird things like move objects into faces and countries. It understands the concept of chips that are about to fall off the table. It understands the concept of a land animal versus a aquatic animal, and so on. But it doesn't understand. It works 20% less good if the background is different, or it doesn't know how to screw a light bulb, or it doesn't know how to like move its arm in a way that it's not straight down, pick up, and straight up. Right, so it's still not generalizing in action and joint space. It's only generalizing in kind of semantic and kind of like visual understanding space. But even just that is still super impressive. Can't wait until you can talk to your car and refrigerator. Very excited to have my own Wall-E in my house. Yeah, you want to know, I actually thought about this. You want to know another weird, crazy thing to think about is that let's say you have a home robot, right? Once you have a home robot, where is that robot going to be? And here is my guess. I think the robot is going to be in your dishwasher hole. So underneath your sink counter, you have a dishwasher, right? And right now, if you had a robot that could just clean the dishes for you, you don't really need a dishwasher, right? The robot cleans the dishes for you. So what if you take out your dishwasher and you have a little robot that kind of like crawls in there, kind of like a droid in Phantom Menace, right? And it just crawls into that hole and it charges itself. And then it comes out and it does its things, and then it crawls back into that little hole and charges itself. Right? I don't know. Kind of like this, you know? It's roughly the size of a washing machine. Everybody already has a little hole for the washing machine. There's a plug down there so it can plug itself. I don't know. That's my guess as to where the little robot will sit. But yeah, that was the paper. Pretty cool work. I think it's a very exciting time for robotics. I think we're years away from this stuff really just being in your house, and the manufacturing is just, it's there. You know, it's like these robots are going to be less than $10,000, especially once we can get rid of these laser scanners, because we're not going to need them, right? I don't know. I'm excited. Thanks for the session, guys. Thanks for the questions. Krista, Fur, Luke, Ed, Kalina, Day, everybody else who asked questions, Regini. Thanks, everybody. You guys have a good time. I think tomorrow we're going to be looking at some pretty gnarly math, so get ready for that. This one, scaling EMA. I don't know. It's not necessarily the most popular paper, but it's been a while since I've done any exponential moving average, and I was like, I have no idea what the state of the art is, so I figured, hey, this is a state of the art EMA paper from Apple. You know, they're probably going to have all the latest tricks and all the latest crap, and basically, if we read this paper, the understanding that we're going to have of EMA and all the different things that go into it is going to be way better. So that's my goal tomorrow, is to come out of this with a much better intuition about EMA and all the actual math that goes behind it. So if you're interested in that, if you're interested in this kind of fucking next level math here, look at that. You got theorems. That's how you know your paper's cool. You got theorems here, corollaries. But it's going to get hairy, so if you're interested, tune in tomorrow. If not, we'll do something else on Wednesday and Thursday. I have a new TBD thumbnail. Look at that. It's like little cats in construction hats. It's very cute. But yeah, stream on Wednesday and Thursday. Tune in if you're interested. If not, thanks everybody, and see you guys later.